It's time for more tweens. Right, ladies and gentlemen, we're gonna do some more tweens. When we last left, we only had a couple of tweens that we were looking at, or that we had finished, one of which was our standard linear tween, and the other one was this quadratic with that in suffix, which ended up means that at the end or at the beginning, start out slow, we'll ease it in, and then we speed up at the end. Then the next logical one would probably be some kind of quadratic out, right? Let's go ahead and create a start for that one. So we'll put our code right in here. So look at this. See this? This in, you look at this curve and it kind of bulges inward or downward, whereas this curve bulges outward. So we need something, because remember, we're dealing with something that starts at 0 and ends at 1, and that's all we want for our ratio. Because at 0, that means that we're starting, and our difference, the difference value, remember that we were adding here, is going to be 0, and then when this ratio is 1, that's going to be the full difference, which from plus that difference is going to be that final value that we want right there. So we want to make this quadratic out ease. So we want it to start at 0. So if we just did t, where t equals 0 to 1, that's linear. That's just going to be plain old linear. So let's say where t equals t times, so we want it to start at 0, so, and then we want it to end at 1, and the quadratic n was t squared, so we need something like 1 minus t, so that would be, multiply that would be t minus t squared. Let's see what that looks like. Okay, so, okay, look. This piece right here, you see the bulge is kind of out. This ease out, which is what we're looking for. But it looks like we go back down to 0, because that makes sense. When t is 1, you have, in here you have 1 minus 1 times 1. So really this needs to be 2, so that when t is 1, you have 2 minus 1 is 1 times 1 is 1. Let's see what that looks like. That should give us half of that curve, which is, I think, what we want. Yes. Okay. So then let's put that in here. That would be ratio times 2 minus ratio. And we want to return that. Just like that. And then let's go ahead, thinking here. Let's go ahead and add our little capability to switch these so that we change this label so that we know which tween that we're doing when we do a tween. And let's change this, and let's call it tween 2. Just thinking about that naming. I really hate to do that. Just another thing to type. We'll just leave it for create for now. Okay. Let's get to the naming of this thing. So what we'll need to do is, instead of, in our tween test, instead of specifying it like this, we need to make a variable. So we'll call it local ease function. And and then we can we'll set it to something up here. Let's say equals tween dot quad. We haven't tested quad out yet, so let's test that. And then we'll just call the easing functions here. Let's test it real quick and see what quad out does. Again, it should accelerate more quickly at the beginning and then slow down near the end. So let's see if it, oh yeah, it certainly does. That looks good to me. So the other thing that we want to do is we want this label to reflect which tween it is that we're looking at. Now, we have a reference to the function, but the function is not going to contain a name because really the function is just a pointer to some stuff in memory. We don't really have a name, but we can, since we have this tween table, and I know this is not the cleanest thing in the world, but we're not looking for performance right now. We're just looking for something to do some debugging and just kind of showing us what's going on. Sort of a tween, well, a tween test scene, as we named it. So let's do a for, and let's do a key value thing. So K would be the key, and V is the value. And we'll do the pairs function, pairs of the tween module. And then we'll do some stuff. So we're really just going to say, what we're going to do is we'll say if the value, in other words, we're looking through all of these things inside of this tween table, which includes really, for the most part, actually, in its entirety right now, all of them are all functions. We're going to look and see if the value is equal to our current ease function. Okay, stay with me. If it is, then we can set that text label to equal our key, which is going to be the name of the function as it was stored inside of the table. Brilliant, right? Huh. And then we can break. And we'll say end. Now, this is being repeated every update. It doesn't necessarily need to be, but this is just easier. And plus, like I said, we're not worried about performance here. Let's see if this actually works. I got it right. Yes, look, see, it says quad out. And that is indeed what it is. Now we need a way to change these functions. So do we just rifle through them, or maybe we have a sort of a table up here that has them all in it, and we have a something like, we press a key, say I kind of like the period and the comma, so we got a greater than and a less than. So like the period would go up. So we would need something like local I know I'm getting ahead of myself here. Sort of. We really want these, and we don't want create, we don't want update. So we could kind of build a little table so that we don't have to keep coming in here and adding stuff whenever we add another tween function. We could say, let's call it available tweens equals an empty table. Let's create a function, and let's call it get tweens. And what it'll do is basically the same thing here as we're doing here, and go through all of those things inside of this tween module. And we can do some additional things. I don't think that we will have anything other than functions inside of this table. But let's go ahead and be nice and say if the type of this value is equal to a function, then that's when we want to look at it. So if this value that we're going to iterate through all these things inside of this tween table. And if it's a function, we want to look at it. And then we want to say if the key is not equal to update and key is not equal to the other one was create. So right now we only have those two in there. So if that's the case, then let's add that to our available tweens. Let's add that tween. That's got to be a tween function, because that's all we have in here is these two functions plus the tween functions, which is what we're looking for. We'll add those here, and I spelled it wrong. Available tweens. And then we do how many are in it, plus 1 is equal to the value. And then we don't, of course, need that. That was from the copy paste there that we just did. I think that's good. And then we can do the following. We can say get tweens. We just get them here, and it will fill up this available tweens. And then we'll do local. We'll call it a tween index, and that will index us into these available tweens. So what we'll say instead of e's function, we'll just say available tweens of tween index, like so. And then we'll come down here and we'll say that. So we're going to be looking for that. So this e's function goes away, and then we have this just available tweens that we store. We're storing all the tweens in here, and that way we can just say, where is our key? Period here. Then we can say tween index equals tween index plus 1. And then we can say if tween index is greater than available tweens. I'm so used to putting those parentheses. Then we set the tween index equal to 1. And we'll make that a multi-line if, just so it looks nicer. Let's see if this actually runs. Okay, so we're set on linear. If I hit period, oh yeah, period is also for change. It's for change scenes. Was that in main? Yeah, see, right here. Let's comment that out for now, because I want period to change our tweens. So let's do this again. Hit period. Tween index equals tween index plus 1. Let's see how many available tweens we have. I'll turn on debug. We'll come up here and we'll print star available tweens. See what that looks like. And I'll bring the, as it runs, I'll bring the, and that's correct. There should be 3 in there. That's what it says. There are 3. That's how many we have, ladies and gentlemen. How many we have. Let's look at this again. Aren't we changing? Oh, I spelled it out, didn't I? Period. No, I want just period. Just a. Sorry about that. Now, quadratic out, quadratic in, and if we hit it again, it should go back to linear. Yeah, that's what I want. I like it. I like it. Let's go ahead and do the reverse so we can go up or down. So period goes up, and then we'll say comma goes down, -1, and then if tween index is less than 1, then tween index equals available tweens, or the size of available tweens, or that length. Let's try. I'm going to go down, and we should get what is it? Quadratic in. Yeah, see? So we can cycle through our tweens that way, and then we can test them by pressing the space bar. let's do an additional thing. So we're creating a tween here. Now let's do this. If, let's say, if position.x equals 2, say if it equals 0, then do this, then create this tween to go to 200. Otherwise, we want to go the other way, which is back to 0. So we want to be able to go both ways depending on where that position or that x position is. Let's go back to 0. So if we press it the first time, we press it again, it'll go back. And then we can change the tween to quadratic out. And then we can change the tween to quadratic in. Yeah, that's what I want. That's what I want. Okay. So what we need now, let's see if we can't. I'm going to copy this. We'll remove this. And we're going to try to create quadratic in out. Now, if you look at some of the tweening libraries out there, they do some hokey, crazy, weird, kind of strange stuff for this one to kind of get these two pieces together. It's apparently the in-outs are a little bit more involved, especially when you're just looking at the ones that are to the powers. So I don't really want to do that. I was playing around with this some, and I found that, and now while this isn't really a quadratic in-out, this is all creative license anyway. We're just kind of doing what we want to do. This particular squared function has the correct look of this ease in out quadratic, right? But it's not quadratic. You get that, right? Not quadratic. But I want to use this for now. Just for now. We may come back later and play with this. I don't like having a bunch of if. I think these easing functions should be fairly simple as far as what they return. And again, if you look at this at some of the way that some people have implemented these easing functions for the in-out for quadratic, and for the others, it gets pretty. I don't know. The math just gets more ugly. There's if statements and things of that nature, and I don't want to do that right now. So we're just going to do this one. And we're going to do it like this, like I just showed you. But we'll say, note, this isn't really a quadratic. Oh, this isn't a quadratic function. But it has the same shape. Now, it turns out that these ease in quad, ease out quad, ease in cubic. Remember what I said? The quadratic is that term squared. Cubic would be the term cubed. Quartic is the term to the 4th power, and quint is the term to the 5th power. It's just a more pronounced, as you can see, jump as you go up in power. Versus, see, the cubic is a little more gentle than the quint in both cases, and it's even more pronounced the quint is than the quadratic. Turns out we should be able to do these pretty easy because these are just going to we'll take the quadratic, and if we want a cubic, we could say cubic in, and this is just going to be to the 3rd power. That's all it's going to be. I'll show you. Come over here, we'll raise this to the 3rd power, and it's going to be exactly what we want. See the easing function here. So it's always that curve that's sort of bulged out downward. I wonder if there's a way to do 2 plots. Let's see. Wolfram alpha. Compare 2 plots. Can I do 2 plots? How do I do that? Multiple function plotter. Or do I have to plotting in graphics? Let's see. Functions, plot a function of one variable. I want to plot two functions. Plot several. Okay, so it's commas. Let's see. So we plot. Let's see if this works. Plot t squared, which would be the quadratic, versus that cubic one. We should be able. Let's see if it'll do it. Oh yeah, look at that. Oh, I love it. So you can see t squared is closer to linear than the cubic one. So it gives you a little more of a kind of an abrupt kind of deal here. And then we can even go t to the fourth. And let's just go ahead and go all out and go t to the fifth. Sometimes you'll see in the easing functions they'll call t to the fifth or the ratio to the fifth. They'll call that the strong easing. Strong in, strong out, and then strong in and out. So that kind of should give you an idea of what's going on there. See, the 1 to the fifth is really kind of stays low here until, maybe about halfway, and then it starts to increase a little bit, and then that last, maybe 20% or so, it just kind of ramps right up there. So we're increasing the bulge of that function, or of that ratio, or that function for the ratio as we increase these powers. I mean, we could do something crazy and go to the 10th power, and you'll see where it really just kind of bulges way out there, and it's almost like more like a step function where it's 0, and then it just kind of ramps up to 1 real quick with that. But these are your typical functions right here for whenever you see an easing or a tweening library. This is what they'll have. So these ease ends are no problem. They're pretty simple. So we'll go cubic, quartic, and quint in. So we've got those. Those are no problem. Let's check those real quick and see if they work. So we got quad in out, quart in. Wish they were in order. Cubic in. So we get that, and we'll go back with cubic in, and then we'll go quint, which is the 4th power. No, that's the 5th. Quartic. See how it starts slow and it really speeds up at the end. And quint. So it starts slow, speeds up even more. So there you go. So the end functions, not too bad. They're not too bad as far as figuring out how to get those to work. What are we sitting at here? We're 22 minutes. Okay, so we're okay. Or 22 minutes, something like that. So we need a couple of more here. We need the cubic in, we need the cubic out, and then the cubic in out. So now we need something that looks again, we reverse that bulge. And if we look at the quad out, oh, and let's move the quad. Let's keep them all together as far as types, like that. So if we look at this quad out, let's see how might we do the cubic out? That's just going to be maybe ratio times, let's see what happens if we just do 2 times ratio times ratio. Let's check it in our heads here, and that would be when ratio is 0, everything's 0. When ratio is 1, everything would be 1. What does that do? And I need to do a return. So we want cubic out. Cubic out. Yeah, see, it didn't look exactly right. And actually what we should do is we should be checking this on Wolfram Alpha. So let's see. If we do t times 2 minus t squared, which is what we're looking at here. Yeah, so you get this little bulge back down to 1. So it kind of actually goes up and then comes back down. Do we have, actually, you know what? Is there a function that does do that? Ease out back. Isn't that what that looks like? It does. It kind of looks like that. Let's do this. Let's take what we have here and let's say let's just do that. We'll comment it out, but we may come back to that one because it does go above 1 and then it comes back down, which is what we want for that ease out back as we create these things. Okay. So, well, we'll go back to, again, 4 from alpha. Let's think about this. If we want everything to start at 0. What would t minus 1? So when t is 0, we would be at minus 1. And then if we squared it, we would be, t at 0 would be 1. And that would go down, which is not what we want. Let's go with this for a second. See, that's the wrong way. So then all we'd have to do would be to subtract it, I think. Oops. That's not what I want to do. I just want to run the function. I want to graph. That's yeah, that's more what we want, but we want it cubed. So is that, oh yes, this would become negative. So within, since we're cubing it, it doesn't. So then maybe we want to add 1, because see, when we say when t is 0, we have negative 1 cubed, which is negative 1. So we want to add 1 to it. And then when t is 1, it's 0, which add 1, and it becomes 1. We may have it. I think we have it. Yes. That, I do believe, is what we want. Let's do a comparison. Let's compare that. Well, let's implement it real quick. That was the cubic out, right? So then we would do return. That would be a power of ratio minus 1, and we want to cube that, and then we want to add 1 to that so that we come out correctly. So let's compare that just to make sure that it is this is more bulgy, if you will, than the quadratic out, which the quadratic out was here, which was t times 2 minus t. So let's compare those two. Yes, and you can see where it is more, it bulges more. So this, yeah, nice. So there's cubic out. I bet, I'm just going to bet that quartic out to the 4th is going to look a lot like this, except we won't have to add 1. Let's see. Let me get rid of all this, and we'll say let's just do that. Let's see what happens when we do that. We'll say t minus 1 to the 4th power. So let's check it. When t is 0, it would be minus 1, and when t is 1, it would be 0. So we want it the other way around, so we need to put a 1 here, I think. Or actually, that would be a minus. Yeah. By Jove, I think we've got it. So the cubic, or the quartic, I'm sorry, the quartic out is going to be 1 minus ratio minus 1 to the fourth, and we also need to do this. Sorry, forgot about that. That needs to be to the fifth. Okay, so did I get that right? Quartic out is 1 minus ratio minus 1 to the fourth power. Let's add these other ones back in and make sure the bulge of that quartic is even more prevalent than the, and it is indeed. So that is correct. I think that's right. That looks good anyway. Let's press our luck and do the quint out. I would think that the quint out is going to look like the cubic out, only to the fifth power, right? So let's check that by adding that to our little set of equations. So we'll do the just plain old, oh sorry, no, sorry, that's wrong. I need to do the cubic. So that would be t minus 1 to the fifth, and then we add 1 here. So check that. When t is 0, minus 1 to the fifth is minus 1, plus 1 is 0, which is what we want. And t is 1, we go to 1. So that, I think, is correct. I mean, it makes sense. Yeah, check it. See? Even more of a bulge. That is exactly what we want. Beautiful. So cubic out. We can grab this because we got odd, even, so that's why by our little pattern kind of changes here. So we'll return, for quint out, we'll return that. So since it's odd, it's going to be a -1 here. That's why we need to add 1. And then this one is even, so it'll be a +1, so we need to subtract it. Quartic, and then cubic, and then quadratic, which is the same, you see. Yeah. Let's check these out. We'll check quartic in, and we actually already checked that one, didn't we? Let's check quartic out. You see how it's fast at the beginning and slows down at the end. And then we got the quad in out, which we say really isn't a quadratic function right now, but we'll change that later. The quint in should start out slow, go fast, and then quint. We want quint out, which is gonna, yeah, that looks good. Let's do this. Let's comment that out. Because we'll have to figure those out here. What are we looking at? 33 minutes. We'll have to figure those out next time. Quint. So the ins and the outs are fairly simple. Let's try one more. Let's do a sine. T dot sine in ratio return something and then it'll be out. And with that, we're going to need, you don't have to do this, but it's nicer to not have to type math.sine. Plus, it's supposed to be a little bit faster. Okay. Let's head over here to our trusty web page here, and we'll get ready to do some graphing. Let's look at that sine real quick. Where is it? Ease in sine. So, ease out sine. Let's do a sine of, let's do t times, let's say pi over 2. because that should, yeah. So from 0, basically sine of 0 is 0, and then when you get to pi over 2, you get that, the peak. So that'd be from 0 to 1, and that looks like our ease out sine. So there's our ease out sine. So let's also do the following. We need to make a sort of a constant, if you will, which isn't really a constant, still a variable, but we'll call it a constant, which is math.pi. We'll just call it pi. So that is, again, what did we say that was? That's sine out. So that's return sine of t, or ratio, times pi over 2, which are 90 degrees. Let's check it real quick. Quint, cubic, quad. There's sine out. Yeah, that looks good. And remember, sine out is that nice start here. Let's try to get ease in sine. So get down and up. Let's see. That would be, we'll probably use, let's see, cosine. Let's see about, yeah, the cosine is 90 degrees out of phase. So I think we could use the cosine here. Actually, we should check it here. So cosine of the same thing is going to change it. It's going to look different because we're going down from that, which is, we want this, but we want something like 1 minus the cosine. And I think that'll give it to us. I think that gives us what we want. Ease inside. That's, yeah, that's it. So we're using the same pi over 2 from 0 to pi over 2 basically, and since the cosine is 90 degrees out of phase with the sine, we get, well, we get that other half of the sine wave or the cosine wave, and then we just subtract that from 1, and then we get what we want. Beautiful. And so we got 1 minus cosine of ratio times pi over 2. And I like to space them out nicer. Let's see what that does. So we got sine in, sine out. We want sine out. Yeah, that looks good. And let's go ahead and create sort of a placeholder for sine in and out. Oh, let's look at that one though. Let's look at that one. I know we're pushing 38, 39 minutes or whatever. This, look at that. Look what it looks like here. This, I'm trying to think. Should we go the other way, or we could do the sine? At this point, it could be either one, I think. Is that right, or will we have to? Because if we went, check this out, if we went -1 to 1 for the sine, then we get what we want, which is this curve. But we are too far. So what that means is we could do 0 to 1, and then instead of pi over 2, we could just do pi, because that's really what it's doing. It's from 0 to 180 degrees. We get this. So not a complete revolution, but we also need to offset our t. So at 0, we want to be at that negative pi over 2. So when t is 0, we're at negative pi over 2. So we get that negative piece. So we're kind of just offsetting it. See? Then we'll also, since we're at -1 to 1, we need to add 1 to it. So we get it up to positive. Boom. But it's too big. So then we can take, that's easy enough to fix. We can take this and we can We can divide it by 2 or multiply it by 0.5, whichever one you want to do, and that should get us what we want. That's not quite 0 there. 0.5. Let's try to multiply by 0.5. Let me pull this back in here. And actually, we really don't need that exactly. We just want to multiply this by 0.5, I think. Or the whole thing. Yeah, sorry. It's the whole thing. So we just say 0.5 or divide it by 2, whichever one. And then we get what we want. See? That is exactly what we want. Beautiful. That's beautiful. All right. So sine in out is going to be, what did we say? The sine of ratio times pi minus pi over 2, because we want us to start over there in the negative quadrant. And we want to add 1 to that. And then we'll take this and we'll divide it all by 2. I think that's right. Let's try it out real quick before we close down this episode. So sine in out right here. So it should be slow at the beginning and then slow at the end. Oh, that looks so nice. I think we got it, people. All right. And next time we may see what we can do about we may already have a little bit of the back function. Which one was it? The out. We may have already sort of stumbled upon that one. We may look at the elastic one, maybe the bounce. The bounce, I'm kind of thinking how we might do that. I kind of have some ideas about that one. But we'll see. So we'll probably continue this next time. But until then, thanks for watching.